Hello, everyone, and welcome to our module on dead space. So dead space is a very important concept in pulmonary physiology. And in order to understand it, let's first talk about minute ventilation. So minute ventilation is the volume of air that moves in and out of your lungs each minute. And it's equal to the tidal volume, the volume of air that goes in and out of your lungs with each tidal or quiet breath, times the respiratory rate. So for example, if a person had a tidal volume of 500 cc's per breath and they were breathing at 12 breaths per minute, this would be a minute ventilation of 6,000 cc's or 6 liters per minute. And a normal minute ventilation is in the range of 5 to 8 liters per minute, depending on a person's body size and other factors. But to understand dead space, you have to appreciate that not all of that minute ventilation is useful for gas exchange. The portion of the minute ventilation that goes to the alveoli, which we call the alveolar ventilation, that is useful for gas exchange. But some of that ventilation goes to dead space, which refers to portions of the lung that do not participate in gas exchange. And so the ventilation going to dead space is wasted in terms of gas exchange because it does not participate in gas exchange. So dead space refers to space in the lungs that fills with air during ventilation but does not participate in gas exchange. And there are a couple of subtypes of dead space. Anatomic dead space refers to space or volume within the lungs that fills the conducting portions of the respiratory tract. So areas like the nose and the trachea, these areas fill with air during ventilation, but they don't participate in gas exchange, and they're part of the normal anatomy of the lungs, so this is called anatomic dead space. Physiologic dead space, on the other hand, is the anatomic dead space plus some alveoli that hold a volume of air but don't participate in gas exchange. So physiologic dead space includes alveolar dead space, which is volumes of air that fill the alveoli. They should participate in gas exchange, but for one reason or another, those alveoli are not exchanging gas, and so that contributes to the physiologic dead space. These are basically areas of the lung with insufficient perfusion of blood, so even though they're alveoli, they are gas exchange units, they don't have enough perfusion to participate in gas exchange. And the apex of the lung, the top portion of the lung, receives relatively little blood flow, so this is the largest contributor to the physiologic dead space. And so your anatomic dead space is essentially fixed based on the size of your body, but the physiologic dead space goes up and down in many disease states. So just to make this very clear, let's look at this drawing here. So anatomic dead space is relatively fixed, but alveolar dead space can go up or down in disease states. Even in healthy lungs, there's some alveolar dead space, especially around the apex of the lungs, but the amount of alveolar dead space can go up if you have a disease process that renders some alveoli unable to conduct gas exchange. And then the total dead space we call the physiologic dead space. And it turns out that it's very hard to measure these things independently. It's very hard to determine just the anatomic dead space or just the alveolar. So most of the stuff we're going to talk about in this video refers to physiologic dead space because that's something you can usually calculate if you know the concentrations of gas going in and out of the lungs. So that's a nice segue into how we measure dead space. And this is done through Bohr's method or Bohr's equation, which is shown here. This is an equation that can determine the physiologic dead space, the V sub D. Remember what I said, it's hard to figure out the subtypes of dead space like anatomic versus alveolar, but we do have ways to determine the total or physiologic dead space, and that's what Bohr's equation allows you to do. Bohr's equation depends on a couple of different variables. First, it depends on the tidal volume, the V sub T, and we can measure this fairly easily in individuals during experiments. And then you need the partial pressure of carbon dioxide in the expired gas, and this is also something we can usually obtain through experiments. And then lastly, you need the partial pressure of carbon dioxide in the arteries, and we can get this from a blood gas. So you take an arterial sample of blood, you measure the partial pressure of carbon dioxide in that blood sample. And so from these three fairly easily obtainable variables, Bohr's method allows you to determine the physiologic dead space V sub D. So let me pause here and review some nomenclature that we use when we're talking about partial pressures in pulmonary physiology, because this can be confusing. So if you think about an alveolus here, we have pressures here inside the alveolus for various gases, and then we've got blood flowing past the alveolus in a capillary, and there's also a partial pressure of gas in that capillary blood flow. So when you see a P with a capital A next to it, the capital A stands for alveolar. So this is referring to the partial pressure of alveolar gases. So for example, P big AO2 means alveolar O2, and P big A CO2 means alveolar CO2. It's the partial pressure of gases inside the alveolar space. When you see a lowercase a little a, that's referring to the arterial partial pressures of gases. So P little AO2 means the pressure in the blood here in the arterial system after it's passed through the lungs for oxygen. If you see a P little a CO2, that's the arterial CO2 partial pressure. And then sometimes you'll see a P sub V. This refers to the venous pressure, so the partial pressure of a gas in the venous system, different from the arterial system. And then when you see a P with an E next to it, that refers to the expired partial pressure of a gas. So just to make this super clear, let's go through this little cartoon I've made on the slide here. So this is an alveolus, and this is a pulmonary capillary here. We've got venous blood flowing into the pulmonary capillary. It's coming from the venous side of the body. It's relatively low in oxygen and relatively rich in carbon dioxide. And over here, we have blood that leaves the pulmonary capillaries. So it's relatively rich in oxygen and it's lost some of its carbon dioxide. It's given it off to the lungs to be exhaled. So the air we inspire from the atmosphere has no CO2 in it, essentially. So the PI CO2 for inspired gas is roughly zero. Once we get to the alveolus, we do have some CO2. That's because the gas inside the alveolar space is picking up carbon dioxide from blood in the pulmonary capillaries. So inside the alveoli in our lungs, a normal partial pressure of carbon dioxide is about 40. That's the P big A CO2. But the funny thing is, if you measure the partial pressure of carbon dioxide in the expired gas coming out of our mouth, it's not 40. It's fallen to somewhat lower, like 35. Why did this happen? That's because of dead space. That's because this gas that we exhale is a mixture of gas coming out of the alveoli, which has a partial pressure of carbon dioxide of 40, and dead space gas, which did not participate in gas exchange and has a partial pressure of zero. And so when the dead space and the alveolar ventilation gases mix, we get an expired CO2 concentration that's lower than what you find in the alveoli. And then finally, out here in the arteries circulating in our body, a normal P little a CO2 is about 40. And that's because the blood equilibrates between the alveolar gas and the pulmonary capillary. And so when blood enters our arteries and leaves our lungs, it usually has a PaCO2 that's equal to the P little a CO2, and that's because equilibrium has been established. In another video, I talk about how diffusion of carbon dioxide is perfusion limited, and for perfusion limited gases, you get equilibrium when you expose the gas to the alveoli by flowing it through the pulmonary capillary. Okay, so back to Bohr's equation or the Bohr method. This is a way of describing physiologic dead space. And we talked earlier about this equation. And now from the last slide, we should understand what P little a CO2 is and PE CO2 is. And so one thing you could do with this equation is actually plug numbers in and calculate a volume for dead space, but it's very unlikely you're ever going to be asked to do that. What you do need to understand, especially for STEP exams, is what happens when the amount of physiologic dead space goes up or down in disease states. That's what they're going to want you to get. So let's imagine we have a perfect set of lungs with zero dead space. Well, then through Bohr's equation, this V sub D would be zero. So this whole side of the equation would be zero. If you remember your algebra, then that means we can cancel out this denominator here and we get that zero is equal to P little a CO2 minus PE CO2, or that the expired CO2 is equal to the arterial CO2. And so the reason I showed you this is not because you need to memorize all this math. It's so that you can appreciate that when we have decreased dead space and we approach zero dead space, our P expired CO2 approaches our PA CO2. There's more gas exchange and less retained CO2. Let's go back to this drawing. Remember we said that we have 40 for a partial pressure of CO2 in the alveoli, but 35 in the exhaled gas. And that's because the exhaled gas has the alveolar CO2 being diluted by dead space gas with no CO2. Well, if there were no dead space, then we would essentially exhale gas with the same concentration of CO2 as we find in the alveolus. In other words, the PE CO2 would become equal to the PO CO2. So that's the first principle to understand related to Bohr's equation, which is as the amount of dead space goes down, the expired CO2 approaches the alveolar CO2. Now let's flip the tables and talk about what would happen if we had 100% dead space. In other words, if the lungs didn't work and all the areas of the lungs were dead space. Well, in that case, VD divided by VT would be 1. In other words, 100% of your tidal volume would be going to dead space. And so we can work through this math here then, which you can do if you want, but you don't have to do this for your board exams. You just need to understand the principle. And we would get that the expired CO2 is equal to 0. So this is another big picture principle of Bohr's equation, which is as the amount of dead space goes up, the expired CO2 approaches 0. There's less gas exchange, more retained CO2, so you're not breathing out or exhaling any CO2. So once again, back to this drawing, we inspire air with essentially no carbon dioxide in it. And if the lungs were all dead space and there were no gas exchange, then we would exhale air that also had zero carbon dioxide in it. And that's the idea of what happens when the amount of dead space goes up. So a lot of students stress over Bohr's equation, find it confusing, but really just the big picture points are what matters most. Understanding what happens when we approach zero dead space or when we approach 100% dead space, because in different disease states, the amount of dead space goes up and down. Okay, now let's talk about what happens to oxygen when there's dead space. And in order to understand this, I've made a little cartoon here, which has two alveoli, one here and one here, and they both have blood flowing past the alveolus in a pulmonary capillary. Okay, so the venous blood that enters our lungs and flows through our pulmonary capillaries has an oxygen saturation somewhere around 70%. So both of these capillaries are receiving blood that is about 70% saturated with oxygen. And then if the lungs are working, that blood will become fully oxygenated or 100% saturated with oxygen after it passes these alveoli. And then the different alveoli will have their capillary blood mix, and the blood that comes out into our arteries will be 100% saturated with oxygen. So this is the normal state, and hopefully this makes sense to you. Now let's consider what would happen if one of these two alveolar units was converted to dead space. So let's imagine we have some obstruction to blood flow through the capillary on the left side. This means that the blood enters 70% oxygenated, but it doesn't pass the alveolus, so it never delivers any carbon dioxide to that alveolus. So this alveolus here on the left is going to have a PaCO2 of 0. On the right side, however, everything is working normally, so blood gets oxygenated just like we said before, and we will deliver some carbon dioxide into this alveolus, and it will eventually have a partial pressure of carbon dioxide that's normal around 40. Well, what happens to the blood when it comes out of this system right here? Well, we get zero blood from the system on the left, and we get all the blood from the system on the right. And the bottom line is that the oxygenation of the mixed blood coming out of the two different alveoli is going to be normal in terms of oxygen. There will be no hypoxemia. So this is a super important principle of pulmonary physiology, and that's when dead space occurs, there usually is not hypoxemia. In general, dead space is not a cause of hypoxemia. The main problem with dead space is that you need all your alveoli to properly exhale carbon dioxide and eliminate carbon dioxide from the body. So when dead space occurs, like this situation here on the left, it doesn't affect oxygen. The main problem is it raises the CO2 level. It causes hypercapnia. And anytime there's hypercapnia, the body's going to respond by raising the respiratory rate to blow off that CO2. So in disease states where dead space goes up, the main thing you see is a rise in the respiratory rate to increase ventilation. That's a super important principle for you to understand. In general, for the Step 1 exam, do not think of dead space as a cause of hypoxemia. There are rare circumstances where dead space can cause hypoxemia if a huge portion of your lungs is dead space, but those are exceptions and they're not something they're going to ask you about in your board exams. For the purposes of board exams, if they describe a patient with hypoxemia and low oxygen, and they ask you what's the cause, dead space is not going to be the answer. Dead space can cause elevated CO2, it can cause the respiratory rate to go up, but in general, it does not cause hypoxemia. Next, let's talk about the alveolar ventilation equation. This is an equation that can be used to predict the concentration of carbon dioxide inside our alveoli. So first, let's review minute ventilation. We talked about this earlier, but minute ventilation is the volume per minute of air that goes in and out of our lungs during normal, quiet breathing. And just an aside here, but the volume we breathe in is slightly greater than the volume that goes out. And that's because some of the oxygen we breathe in is taken up by our bloodstream, and therefore it's not present in the volume of air that goes out. And just a terminology thing here, but minute ventilation is also sometimes called total ventilation. That's because the total amount of gas ventilating going in and out of our lungs. Different from minute ventilation, though, is alveolar ventilation. So this is minute ventilation if we could take away the dead space and talk about only the volume of air going in and out of the alveoli that participates in gas exchange. So for example, if our minute ventilation was 500 cc's per minute, but 250 cc's or half of that was filling dead space, then the alveolar ventilation would be 250 cc's. This is the volume of air that's available for gas exchange. So shown at the bottom of this slide is the alveolar ventilation equation written in two different forms. And this equation tells us what the partial pressure of carbon dioxide inside the alveoli is going to be, and we can calculate it using all these variables here. And let's just go back to this slide briefly, and I want to remind you that whatever the partial pressure of carbon dioxide is in the alveoli, that will also be the partial pressure of carbon dioxide in the blood in our arterial system. And that's because we always have equilibrium established after blood flows past the alveoli and the blood from the pulmonary capillaries leaves the lungs and goes into the arterial system. So the alveolar gas equation can give us P big A CO2, which is the concentration of carbon dioxide inside the alveoli, but that's going to be the same as P little a CO2, the concentration of carbon dioxide in our bloodstream. So back to this slide, if we look at the equation on the left, it's telling us that alveolar CO2 concentration is equal to VCO2, which is the rate of CO2 production by the body, divided by V sub A, which is the alveolar ventilation, times K, which is a constant. And K is just basically a constant to make the units work out so that the answer you get is a partial pressure. But remember what we said before, the alveolar ventilation, V sub A, is equal to total or minute ventilation minus dead space ventilation. So this equation can also be written as I've done here on the right side of the screen. Now, having gone through all that, I want to tell you that it's extremely unlikely anyone on your step 1 exam will ask you to actually use this equation to calculate a PaCO2. What they're going to want you to understand is what are the variables that can make the CO2 concentration in our alveoli and therefore in our arterial system go up. And that's what this equation tells you. So if the body produces more CO2, that can make the alveolar concentration of CO2 goes up. Hopefully that makes sense to you. It's fairly logical. If our total ventilation or our minute ventilation goes up, then that's going to make this denominator bigger, and that's going to bring down the PaCO2. And if you think about that, it's fairly logical. If we ventilate our lungs more, we're able to get rid of more carbon dioxide, and therefore the partial pressure of carbon dioxide in the alveoli and in our blood is going to go down. In other words, the amount of carbon dioxide in our blood is proportional to how much we are ventilating the lungs. And then finally, if the amount of dead space goes up, that is going to make this number on the bottom smaller, and that's going to raise the PaCO2. And that also should make sense to you when you think about it. If we have a lot of dead space, we have a lot of wasted ventilation, and we're going to be unable to get rid of carbon dioxide, and therefore our P big A CO2 is going to go up. So the most important thing to understand from the alveolar ventilation equation is that it tells you the 3 factors that can make carbon dioxide levels in the blood rise. They're all shown right here in this equation. If the body makes more CO2, then you will have a higher concentration of CO2 in the alveoli and in the blood. If there's more dead space, then the amount of CO2 in the alveoli and in the blood will go up. And if there's hypoventilation, meaning a fall in the total ventilation of the lungs, that can also lead to a high level of CO2. And you can see all these things from this equation right here. Now, one more very important thing, even though I've listed right here 3 potential reasons why you can develop a high level of carbon dioxide, the most important one is the one in the middle that I've bolded in red, hypoventilation. Because when you think about it, if the amount of CO2 production goes up from the body, say for example, when you're exercising and there's more metabolic activity, if you increase your ventilatory rate, then the CO2 level won't rise. You don't develop a high CO2 level when you're running or exercising, even though your body's producing more CO2, and that's because you've raised your ventilation rate. By that same logic, if we increase the dead space in the lungs because of some pathologic process, as long as we can raise our ventilation rate, we can account for that and keep our CO2 normal. So my physiology teacher back in med school used to say there's really only one cause of elevated CO2, and that's hypoventilation. And what he meant by this is even though other things can raise the CO2, if you're able to raise your ventilatory rate, you can blow off that CO2 and you won't develop elevated carbon dioxide levels. And clinically, and for board questions, whenever you see a case where there's an elevated CO2 level in an arterial blood gas sample, one of the first things you have to think about is that that patient is likely hypoventilating and needs to increase their ventilatory rate to stop retaining all that carbon dioxide. This can be a tricky concept, takes a little time to get it right in your head, but if you think about it and get it straight, it will help you with a lot of pulmonary physiology questions. So just to emphasize this point, elevated carbon dioxide in the bloodstream is called hypercapnia or hypercarbia. The 2 terms are used interchangeably. And whenever this happens, this will cause an acidosis, which is detected by chemoreceptors, and the physiologic response is to raise the respiratory rate and increase the alveolar ventilation. And so what this means is that you will rarely see an elevated CO2 level in the bloodstream unless there's hypoventilation. That must be going on to some degree, even though other things could be contributing like dead space and metabolic activity. The patient must also be hypoventilating to some degree if the CO2 level is elevated. And that's what you should always think of when you see a high CO2, is that there must be some form of hypoventilation going on. Okay, I'll finish this video by talking about the alveolar gas equation, which is different from the alveolar ventilation equation. The gas equation is used to predict the alveolar partial pressure of oxygen. So we talked earlier about how we inspire air with a certain partial pressure of oxygen, and that air goes down into our alveoli, and some of the oxygen is picked up by our lungs, and it leaves behind a partial pressure of oxygen in the alveoli, which we call P big AO2. And normally this number is about 100 when you're breathing room air. So this equation right here is the alveolar gas equation, and it predicts the alveolar oxygen partial pressure based on other factors. So according to this equation, the P big AO2 is equal to the partial pressure of inspired air for oxygen minus the partial pressure of carbon dioxide inside the alveoli divided by R. And R is the respiratory exchange ratio. It's the amount of carbon dioxide produced each time a molecule of oxygen is consumed. And it varies with our diet and our metabolic state, but the usual number that's used is 0.8 or so. But once again, it's very unlikely you're going to be asked to actually use this equation and plug in numbers to calculate PaO2. Instead, what they're going to want you to understand are the different variables that affect the PaO2. So according to this equation, anytime your inspired oxygen content goes up, your PaO2 goes up. And hopefully that's fairly easy to understand. If we give you 100% oxygen for PiO2 instead of 21%, which is what room air is, you're going to be inspiring air with a much higher partial pressure of oxygen, and that is naturally going to lead to a higher partial pressure of oxygen in the alveoli. Also, the more CO2 that takes up space inside the alveoli, the less sort of room there is in there for oxygen. And so when our CO2 level goes up, our PaO2 level goes down. And hopefully that also makes sense to you. We talked earlier about how the major cause of P big A CO2 going up is hypoventilation. So if you're hypoventilating, this P big A CO2 number is going to go up. And anytime you hypoventilate, you bring less oxygen into your lungs. So naturally, your PaO2 goes down. So that sort of makes sense logically, and that's also what this equation is showing us right here. So just to make this all very clear to you, I've created a table on the slide, and let's look at what it shows. So when you're breathing normal room air at sea level, the PiO2 is always going to be 150. But what I've shown on this slide is how your PaO2 is going to change based on your PaCO2. So if you're breathing air with a PiO2 of 150 and your PaCO2 is normal at 40, then if you use this equation, you will get a value for PaO2 of 100. This is a normal value for alveolar partial pressure of oxygen. But now let's imagine a person starts to hypoventilate. Anytime you hypoventilate, your PaCO2 is going to start to rise because you're underventilating the lungs and you're not blowing off enough carbon dioxide. Well, if we take this value of 50 and we plug it into this equation down here, you get a PaO2 of 88. And hopefully this makes sense to you. If a person's hypoventilating and it's causing their CO2 level to rise, they're hypoventilating, so they're also going to cause their O2 level to go down. And then in these last three rows, I've plugged in different numbers for PaCO2. And as the PaCO2 begins to go up, the PaO2 begins to go down. And this is all predicted by the alveolar gas equation at the bottom of the slide. And that concludes our module on dead space.